Well, welcome everybody. We're excited that you're here. Thanks for joining us. We have a lot of folks that are going to be joining us as we kick this off. So, always like to start with some announcements. Thanks for being here. This is our 13th webinar in the last 5 years. So, we're excited that you've been able to join us. So just as a note, upcoming webinars right now, we're averaging about 2 a year. If you have ideas or topics you'd like to hear more about, let us know. You can email me, Mark, or anyone at Geoengineers. We like putting these on because it helps not only us kind of prep for something like this and look at what we're doing and share that knowledge outwardly, but also equip all of our colleagues in the industry with our insights and learn from you as well. If you're not receiving the webinar invitations, make sure you reach out to me and we'll get you added. You can always forward the invites when I send them out as well. Upon completion of today's webinar, we are recording this, and so we'll send out a link to the recording. All recordings for prior webinars are also on the geoengineers.com website. When I send out the link, I'll include a certificate of completion as well, and so you can self-report that for an hour to your accreditation organization. If you have questions, go ahead and put them in the chat. Mark will be presenting today, and we have a lot of content to go over, but we're hopefully going to have a couple minutes for questions, and Mark will stop throughout just to see if there are any, and if not, he'll continue to go. You can always reach out after today's presentation as well. We love hearing from you and having dialogue. And just as a disclaimer, we always like to say the views, information, and opinions expressed during this webinars are those by our moderator, myself, and or our panelists, and are solely those of the individuals and do not necessarily represent those of our respective organizations. So we try to say that up front. That way, if someone has a question and you go off mute or you put it in the chat, this is more of a dialogue and conversation. So with that, a lot of folks have joined before. Mark's been a participant in a lot of these panels. He does such an awesome job describing the topic at hand. So I get to introduce him. He's been at Geoengineers 28 years, with 19 of those years focused on trenchless. He's currently our national pipeline practice leader and has worked on hundreds of HDD projects. I always like throwing in a fun fact about him. If you've ever traveled with Mark, he is the ultimate navigator. He is so good at not relying on Google Maps or any map system. So it's just, I love traveling with Mark because he makes my life easier. We're not looking at my phone. So just a fun fact about him. So with that, I'm going to stop sharing and toss it over to Mark, and so he can give our safety moment and then dive right in.
Yeah, thanks, April. Let me make sure I'm sharing the right screen here. So actually, is that the right one?
Yep.
Okay. All right. So let me get my little laser pointer going, make sure you can see that. Okay, so we'll start with a safety moment. Welcome, everybody. Good morning or afternoon, wherever in the world you happen to be. Our kind of company safety motto is home safe every day. We want to make sure all of our employees are safe home every day. They leave home safe and get home safe. Safety is a key component of everybody's workday. And I want to just cover a little safety moment here. And I've got a picture of an HDD site. Maybe not the most, housekeeping may not be the best at this location, but I just like to bring this up. Slip, strips, and falls are one of the most common injuries on construction sites. You can see here you've got an open drilling fluid pit it's not very well barricaded. You've got hoses, hydraulic hoses, drilling fluid hoses all over the ground. You got wood mats back here, and there's gaps in those mats. You really need to be watching where you're going on these sites. Don't be looking at your phone. You have equipment operating, very dangerous. So I guess it's just when you're on these sites, you need to be present. You need to be paying attention to everything around you and where you're going. So today, this is kind of a back to basics thing. This is just a very, for hopefully, it's informative to people who heard about HE, know some stuff about it, but we'll go into this some of these topics a little bit deeper. We'll talk about some things to consider when you've got a project that does include or might include an HDD, some things to think about early on in the project, and kind of go through kind of what we see as say the most efficient and proper way of integrating an HDD into your project. So we'll talk about what it is. We'll talk about the evaluation design process. We'll talk about the importance of construction observation, and we should have some time at the end for some questions. So let's talk about what is HDD. This is a photo from a job I was on in Eastern Europe. So basically in HDD, we're trying to get across an obstacle. In this case, we have a pretty big river here in the country of Georgia, not the state. You've got an HD rig here. This is a little unique. It's actually was dug into an excavation, so it was lowered down because we had to try to get as much depth under this river as possible because of the topography. We had an issue. So let me see here. It looks like I may be sharing my
Yeah,
wrong.
you're sharing. I just want to make sure you knew that you were sharing the slide that shows like the next slide. So you might need to, sorry guys, Zoom is really tricky. We use Teams at Geo, so welcome to technology and getting ourselves
Yeah.
equipped for it.
Well, yeah. Let's see. So I see people's things, and why do I only have one Zoom window?
You might stop share and then reshare for the one.
I can't find my Zoom window. That's crazy.
I think it's showing just that screen, so just FYI.
Yeah, this screen. So
Yeah,
it's
but it
showing
also
the,
shows your desktop if you minimize it.
yeah. What the heck? I've got pictures. I've got pictures of people list of everybody that's on here, but
That's
where?
totally fine. I'm fine with it. If you're on the call, then you just get a teaser for the next slide. So that was pretty awesome. Grady's giving a thumbs up, even though he's driving. He's present. He's excited. I'd say continue forth.
Well, I hope Grady can. Oh, here we go. I got it. Sorry, I'm going to share this screen. All right. Is that the correct? No, let me stop that one. I'm sorry, everybody.
You're totally fine. You had it a second ago. You're doing great.
There we go. That's the one I wanted to show. All right. I'm kind
Nailed
of
it.
I'm kind of a Zoom noob. Anyway, the idea is to drill from one side of the obstacle to the other. In this particular case, to get as much depth under the river as possible. They actually had to excavate the rig down to get some additional depth to cover, and it's just because of the topography at the site. Over here on the other side, we call that the exit side or pipe side. It's where you're going to fabricate your pipe that you're eventually going to pull through the hole. This would be on the exit side during a pullback. You can see they have a bunch of side booms with roller cradles, in this case, some cranes, kind of lift the pipe up, get it oriented in the correct direction for the hole. You can see this one has a horizontal bend as well, so it was kind of a complex lift type scenario, but because of the workspace that was available, it was kind of the only way this was going to work. So let's talk a little bit about some of the terminology and just the design profile itself. So first we have our entry tangent. It's basically just your initial straight section of a drill profile. Typically between 8 and 14 degrees. This says 12, 14, you can go steeper, but that's kind of where we like to keep the entry angles. We like to have an entry tangent. It's, 60 to 120 feet long. That allows the driller, when they first spud the drill bit into the ground, it allows the driller and the pilot hole surveyor to kind of understand how the drill bit's going to react, how it's going to steer in the formation before they have to start steering any curvature into the profile. We've got our entry curve, obviously not to scale because it should be more of a circular arc. We've got a bottom tangent here, just a straight horizontal section. This can be inclined, it doesn't necessarily have to be horizontal, but we typically like at least 120 feet. Now this is on a larger scale, longer crossing, but that bottom tangent allows the driller, so if they're drilling through the entry tangent and through the entry curve, and they can't quite keep up with the curve, the radius of the curve while they're drilling the pilot hole, and they end up a little bit deep or below the bottom tangent, this gives them some distance to try to catch back up to where they need to be before they have to start drilling the exit curve. So we've got bottom tangent, exit curve, and then we have our exit tangent. So those exit angles typically 8 to 10 degrees, 12 degrees sometimes. Larger pipes, you want lower exit angles because in order to lift them up and get them oriented into the hole, you have to lift the larger pipe higher because it's stiffer, needs a larger radius of curvature. So larger pipes, you're going to want to keep your exit angle down maybe 6 degrees, let's say, for a 48-inch pipe. So what I showed in this was very simple, most basic design profile. That's the way you want to do it if you can. If you can't, you can make things more complicated. In this particular example, the St. Clair River between Michigan on the left side and Ontario, Canada on the right side. We had to incorporate 2 horizontal curves to make this work, because the only real estate available on the Michigan side was this narrow strip of property, which the pipeline company had to buy the house and structures, buy the property, demo them. And the only place we could land over here on the Canadian side of the river was over here. So not recommended you do this. If there's no need to, then don't do it. We were fortunate here because the soils were suitable for, let's say, they were good for trying to accomplish something like this, and it went pretty well. So let's talk a little bit about the construction process itself. So we have the pilot hole. So essentially, you're steering the drill bit across underground, trying to follow the profile we just showed you. Depending on the size of the project, this could range from, say, 6 to 12.25 inches, something like that. Just show you the makeup of what we call the bottom hole assembly here. We have a non-magnetic drill collar. You have your orientation sub, jetting sub, and a drill bit. So in bigger scale projects where you have a downhole steering tool, you're going to have the downhole steering tool back here in your non-magnetic steering collar, sometimes called a Monel, which is then screwed into the annular or the orientation sub, which has this annular pressure port in it, which monitors the pressure in the annulus, which is a pretty important factor. It's pretty common these days to want to monitor these pressures. We can monitor those pressures and see how they're going relative to what we'd anticipate. So we can see if the pressures are getting high, maybe we have a downhole problem, maybe we need to trip out, flush the hole out, just circulate fluid, try to get the pressures back where they belong so that we don't frack out or have drilling fluid surfacing where it shouldn't be. We have this jetting sub, essentially just this for soil. In a rock crossing, you would have a mud motor where the jetting sub is located. But for soil, this jetting sub it just has a few degree angle to it. It's usually the threads on the one end are cut at an angle, so it gives you this slight steering bias. And then you have your drill bit. There's different styles of drill bits. This is just your standard tricone. So yeah, you drill your pilot hole from one side to the other. On longer crossings, you can actually do an intersect. When you start getting very long crossings, it can be hard to steer once you get out 4,000, 5,000, 6,000 feet. So you can drill from both sides and meet in the middle. So it's amazingly enough, it still amazes me that that's even possible. But the nice thing about that is about an intersect too is it lowers the annular pressures required to drill the hole, because you're essentially drilling half the hole from each side, keeps your pressures lower, reduces your risk of frac outs. So it's a good mitigation measure for that. And on let's say levee crossings where the Corps of Engineers is involved, it's common to do an intersect just so we can keep the pressures as low as possible. Now this is a natural picture of what we just showed. You got the drill bit, you got the bent sub or the jetting assembly. You've got your orientation sub right here with the pressure port. Hopefully you can see that. There's a pressure port there. And then you have the Monel, which is where the steering tool would be housed. And so, just to let people understand kind of how the drill bit is steered, is the steering tool has a roll sensor in it. And so before they, put this thing down hole, before you spud in, you would rotate this jetting assembly to where it's what we call high-sided or pointed up. And then you reset the roll sensor on the steering tool to be 0 degrees. And in the drill cab, the driller has we call it driller's display, and it's basically 0 to 360 degree clock face that tells him which direction the bit is pointed. So then once this is down hole, he has a constant readout of which direction the bit is pointed. So when you're drilling, if you want to turn to the right, let's say, you could rotate the bottom hole assembly to 90 degrees, tool face to 90 degrees. They turn the pumps on. And in soils, you just let the fluid do the cutting and you push the drill string. You just push it with the drill rig. And that steering bias naturally makes it want to go to the right. Now, if you want to go straight, you just rotate the whole drill string. And go ahead. It takes out that steering bias by rotating the whole drill string. So in that way, that's how you steer these things. It's pretty simple, really. It's not anything too fancy, but it works. Talking about drill bits. This is a tricone drill bit, fairly standard. This is a mill tooth drill bit, be used for soils, soft rock, that sort of thing. You can see there's drilling fluid jet up here. There's one down here that you can't hardly see, and there's another one down here. So the drilling fluid comes out of there, and on a soil crossing, the fluid itself fluidizes or cuts the soil and entrains it into the drilling fluid so that it can flow back out of the hole. Now, in smaller projects with smaller drill rigs, you might see what we might call a duckbill drill bit, maybe 6 or 7 inches in size. The drilling fluid jets here, you can kind of see they're on the top. So different style of drill bit, but they steer really well. This would be more for soils again, but they steer really well. Let's see. I guess we got a close-up of it. Reaming. So once you have the pilot hole drilled out to the other side, you're going to attach a reamer. For soil, you'd use what's called a fly cutter, or for rock, you would use a split bit hole opener, which we'll see here in a minute. Behind that reamer, as you're reaming, you're going to be attaching tail string or joints of drill pipe behind the tool, which is, basically kind of insurance, because if you have a tooling failure in front of this reamer, you have the reamer still hooked up with the tail string. So you could pull this reamer back out the exit side if you had a catastrophic failure downhole. So it's pretty important to run a tail string. Now, if you're in town and they're doing a little road crossing for some fiber or electric, they're not going to do this sort of stuff. Typically, they're just going to drill their pilot hole, hook onto whatever, and just pull it back through. But this is more for larger scale type crossings. So this is a split bit hole opener for rock. I don't remember if this is a 42 inch. I forget. It's been a while, but this has a centralizer ring on it. So this helps the tool centralize itself inside the smaller hole that's ahead of it. And in this case, the contractor was running a secondary centralizer ring in front of that. These tools are heavy, they weigh over 10,000 pounds. And so, the better you can get everything aligned up and that tool faced up, the better it's going to cut. And the less, let's say, stresses on these tool joint connections, particularly in the front. And because, there's a lot of force and a lot of torque that goes into cutting a rock hole. So, having these centralizers kind of helps mitigate some of the wear and tear and just the loads on everything. Once you've reamed the hole out to as big as it needs to be for the pipe, typically about 12 inches larger than the size of the pipe, you're just going to run a swab pass, which is a reamer that's slightly smaller than your reamed hole. And again, you're going to run tail string. And the idea is that, you're just going to flush it out. If there's any accumulated cuttings downhole, you want to try to stir those cuttings up, get them in the drilling fluid and flushed out of the hole. It's also a good way to see if maybe there's some unstable spots in the hole where it may have collapsed, or you have some gravel or piles of gravel that may have accumulated if you have some gravelly soils where you're at, to try to get those either up and into the fluid or pushed out of the way, whatever the case may be. And this is a barrel reamer. So this would be kind of something that you'd use in a soil hole, swab a soil hole or a hole in soil. For a rock crossing, you use a hole opener, like a split bit hole opener, like we were showing earlier. So if there were some rock in the hole, that hole opener could break up some of that material and get it flushed up and out of the way. So, and finally, you've got pullback. So this is kind of a typical pullback assembly where you've got a reamer in front, again, to kind of help sweep out anything in front of it or break up anything in front of the pull section as it's coming through the hole. Got a swivel here, which allows them to rotate the drill string and the reamer without having to rotate the pipe, which is then attached by a shackle to a pull head that's welded to the front of the pipe. And this is a pullback assembly. I don't remember what size pipe this is. It's maybe 42 or 36 or something. You can see you've got your barrel reamer, got a swivel, shackle connection here, and then your pull head. And then this is kind of what pullback kind of looks like. Well, not necessarily in every project. This is a project one of our guys was on in New Jersey. They didn't have a lot of room to string the pipe in one section, which typically you're going to want to do if you can. They didn't have that luxury here, so they had to string the pipe in sections, pull a section in, weld the next section on, pull the next section. Again, not ideal. This was a rock crossing, so in rock crossings, if you have to stop during pullback, it's typically not as big of a deal as it is in soil. That hole in soil is not going to remain open forever, so you need to kind of get this done as soon as you can. So how do they get the cuttings out of the fluid? We're recirculating drilling fluid. The fluid is picking up cuttings from downhole and is returning back to your pit. We need to remove those solids. So this is kind of a typical large drilling fluid recycling system. It's kind of about the size of a frac tank, really. So these bigger systems typically have these shaker beds. There's 3 of them. Each one filters out smaller and smaller particles from the drilling fluid itself. We call this first one the scalper shaker. Fluid just dumps onto the shaker bed, and the shaker bed has a series of screens. There's a screen here of progressively finer sizes. So you can see here you're getting fairly coarse material out. Over here we have the desander. We're getting more sandy material out, and then down here we have what's called the desilter. Desander and desilter have what are called hydroclones. They're very similar to how, let's say, the Dyson vacuum works. Basically, the fluid goes into an inverted cone, and the centrifugal force of fluid going around a circle inside of this cone actually separates the solids from the liquids, where the liquids rise in the cone, and the solids come out the bottom. And so what that looks like on a desander is something like this. These typically have, they typically have these, kind of nuts on the bottom, but they're off of this one for some reason. You see the threads on that. But you can see what's coming out the bottom. It's primarily solids with a little bit of drilling fluid mixed in. It dumps onto the shaker bed, and you can see the screens here. The fluid, these are vibrating. They have eccentrically weighted motors that vibrate these whole things. Fluid passes through the screen into a tank below and gets pumped to the desilter, which works on the same principle, but they use smaller hydroclones to get out smaller particles. So it's just a progressively filtering out finer and finer materials. So let's talk about, evaluating, some of the things we look at when it's like, well, this project is going to have an HD let's look at some of the things we can do from a desktop study perspective. And, Google Earth is great. And this is just something I like to point out is use the history function in Google Earth. You can go back and look at other photographs from previous years. So we were working on a project down in Beaumont or Port Arthur area, and we had an HD that was going to be coming right through here and through this area. And in the 2018 image, it's like, okay, well, yeah, it looks kind of swampy and stuff. But if you go to this 2017 image, you can see that there's a workspace here. If you zoom in on that, you can see a drill rig. And so it's like, oh, okay, I guess we have somebody came in before us and put in another HDD. So these are good things to be like, okay, we need to go to our client and say, hey, look, there's another HDD in here. We need to get the as-built information for that so that we can make sure we provide enough separation between what we're trying to install and what they have installed. So that's important. The aerial photography on Google Earth is great. You can draw a line, cut a cross section. These are good tools to use initially. Obviously the elevation data in Google Earth is not perfect, but at least give you some idea of what things look like. Street View, use this all the time. Most of you guys probably use this a lot. So, but it works great if you have a workspace that's adjacent to a road. One of the things I don't know if a lot of people use, but want to point this out is, different states have a lot of different resources, geology maps, typically like the DNR, Department of Natural Resources, or whatever they're called in a particular state, all sorts of stuff. And we like to look at well log viewers, well log mapper tools online, particularly when we're, initially looking at a job or trying to get a cost to go drill some geotechnical borings. Are we going to run into rock? How deep might the rock be? So we can kind of account for that in our budgeting process. But this can also go towards, if you have an HDD and you're taking a very preliminary look at it, you can kind of get an idea as to how deep bedrock might be. And this is not a lot of detail, but you can see that it looks like they hit limestone or sandstone somewhere around 40 feet. So that tells you a lot more, well, more than you knew before, right? So things like that can be helpful initially during the process when you don't have anything else. Like I said, geology maps. This is a project in Pennsylvania. Pennsylvania has great geology maps. Um, this was a proposed HED crossing, a ravine, a valley with a creek at the bottom of it. And one of the things from the geologic map is you can see all these arcuate black lines here. Those all denote landslides, mapped landslides. So, it's one of those things. Well, if you're going to install an HED, you probably want to make sure you're below any slide mass. You don't want your pipeline being gathered up or destroyed by a future landslide. So geology maps are great. Pennsylvania also has LiDAR available, which, in a hillshade format can give you really nice, and you can give you kind of a really nice image, but you can tell that there's a lot of slope instability along here where those mapped landslides are shown in that previous slide. So geometric design. So we talked a little bit about the basics. Early on, create a conceptual plan of profile drawing. Get some ground surface data, get an image, and figure out, okay, well, how deep might this thing be? And we have these cards, and I think April can hook you up with some. We can mail them out later, but hopefully y'all can see that. We have these cards that kind of give you a cheat sheet on, okay, if this is a 36-inch pipe, your typical length is probably between 14 and 1,500 feet. So you can draw up kind of a simple profile: entry tangent, entry curve, bottom tangent, exit curve, exit tangent. And you can draw something up and you say, okay, well, how deep is that going to be? How deep can we make it given that length? Can we make it deeper if we go longer? And you can put borings on here. How deep do the borings need to be to make sure we characterize the soil profile or soil and rock profile within the depths of our proposed or conceptual HDD. It's always good to get borings that are deeper than you think you're going to need them, because if you go out there and drill your borings, you may find something that's like, man, we really need to make this thing deeper, either to reduce the risk of frac outs, or there's a layer that's got a lot of gravel, let's say, or a fractured rock that you're trying to avoid. Getting deeper borings than you think you're going to need is pretty helpful. And someone might ask, well, how many borings do I need? Well, I don't know. Depends. It's always my answer to that. What's the risk of the project? Is it a 2-inch HDPE line under a city street? You might not need any. It really is relatively low risk operation. Your biggest risk is utility strike. But if you have a long crossing, you're going to need several borings, most likely. You need to be able to characterize the construction risk. How variable are the subsurface conditions you expect? You expect a fairly consistent conditions from one end to the other, then maybe you don't need as many borings. If you expect more complex or less consistent geology, maybe you need more. It just kind of depends. So, there's been cases where what we found, we just said, wow, we didn't expect this. We probably need another boring or two. So get that conceptual drawing put together. So you kind of plan out how deep the borings need to be, where can I put them, make a site visit. What are the access routes to where you're going to have your entry and exit workspaces? The equipment, especially for these bigger jobs, it's pretty big. You need semi trucks and trailers to get in there. What are those access routes look like? What kind of improvements might need to be made to get your equipment into those workspaces? Do you got to are there power lines in your way? Another thing about a site visit, you see these pipeline markers. You may not have any survey from the site or not know really much of anything, but if you see these pipeline markers, well, there's probably at least 3 pipelines in here. So it gives you some things to think about early on, just by visiting the site. What kind of obstructions might you face? These were I think they were installed kind of in the South and, Louisiana, Mississippi, maybe in Texas, to kind of help bank erosion. They didn't really work that well, or maybe they worked, but they got damaged a lot. But are there pilings or other obstructions you're going to have to deal with? Go to the site and look, poke around. This one I like because, I've been on site visits some clients and they don't even want to get out of the vehicle. It's like, well, let's go look at what we're trying to cross. Let's just see what we got. Because if you were standing up here, you'd look at the ground, you'd see all this gravel, and you're like, man, this looks pretty bad. But if you come down to the creek here and you'd be like, oh, looks like it's about 3-4 feet of this gravelly material and there's beautiful sandstone. That's great for drilling. So yeah, look around. You don't make sure you get out of the car. Are there any slope instabilities like earlier when I showed that geologic map with those landslides? Do we need to make sure that we're going to have our HDD beneath any potential slope movements? You definitely don't want your pipe to be within a slide mast. Great time to stake out boring locations, particularly if the site is a long ways away from wherever you're located, stake those out. I mean, there's a decent chance that cows or something could knock them over or whatever, but at least you tried. Subsurface explorations, you can drill borings anywhere. If you're in the marsh, you've got marsh buggies, you can do overwater borings, truck mounted rigs, there's rubber tired ATV rigs, there's even airboat mounted drill rigs. So you can drill pretty much anywhere. If you have to, you can helicopter in a small skid mounted rig to essentially anywhere. Sampling, so typical sampling, it's nothing special about it. SPT samples are typical. Now, when you get into softer soils, let's say the Gulf Coast, you're going to want to use Shelby tubes. When you get undisturbed samples, and we can take unconfined compression strength tests or unconsolidated, undrained triaxial strength testing, so we can understand the strength of the soils. That really helps us estimate the risk of hydraulic fracture during construction. Laboratory testing, again, pretty simple. Nothing really too crazy about it. I guess I should mention rock coring. If you have rock, you definitely get continuous rock core samples. Doesn't really matter the size of the core barrel. Sieves, pretty important. Understand the grain size characteristics of the soils. There's typical sieve chart. Atterberg limits gives you the plasticity index and liquidity index, liquid limit and plasticity index of the soils. Kind of tells you how plastic they are, how sticky they might be. A highly plastic clay is going to be super sticky versus a clay or silt that's non-plastic or low plasticity. So then that helps, like with a drilling fluid engineer, to develop a drilling fluid plan for maybe particular additives they might want to use. These highly plastic soils can kind of clump together or ball up in the hole, the cuttings can, which can then form larger clumps, which then can block the hole, which then causes pressures to go up downhole, which then can lead to frac outs. So it's good to kind of know what you're drilling through. It helps the contractor. There's just an Atterberg limit chart. We have on the left a load frame for doing unconfined compression strength tests, on the right triaxial cell for doing unconsolidated undrained testing. So that's about feasibility evaluation. So this is the same drawing I showed earlier, the conceptual drawing we talked about. So now you can add the borings to it. You can plot those out and you say, okay, on my conceptual profile, what are we going to be in? Is there something deeper that would actually be better, would help reduce the risk of a frac out, or potentially shallower, and in this case, we actually have bathymetry now. And I didn't point that out before, but in that initial conceptual drawing, we didn't have the bathymetry for this here. Obviously it's not that deep, but in some cases, we've been really surprised on projects where we get bathymetry and the river is a lot deeper than we anticipated. So again, another good reason why you might want to consider deeper borings than you originally thought. It's cheaper to drill 20 feet, an extra 20 feet in a boring while you're there, than have to go back and get more later. So, kind of so what are the things I've already kind of talked about a little bit. Gravels, gravels, with an HED, you need to try to maintain a stable hole, right? And, gravels, if there's not a lot of matrix material, sand and silt, clay, it's just going to want to collapse on you. I mean, imagine trying to drill through a bunch of bowling balls. You're not going to be able to keep any kind of open hole. Now, if it's mostly sand and silt and it's got some gravel in it, maybe some big gravel, but it's occasional, maybe not a big deal. But something to consider. And then I was talking about clays, highly plastic clays, very sticky, and understanding that. So hopefully a mud engineer can help develop a drilling fluid plan that will work better in those types of materials. Because we talk about frac outs. What's the risk of a frac out? Not only is it a pain because you got to clean it up, but it's non-toxic. It's 97-8% water and 2 to 3% bentonite, but it makes a mess. It slows things down, and regulatory agencies don't like it. And particularly if it's in somebody's yard. I've heard stories of drilling fluid fracking out into people's basements. So understanding subsurface conditions, monitoring your pressures while you're drilling, maintaining your returns are very important. So talking about HE evaluation design phase. So just talk about kind of what a typical HE drawing might look like. Again, another plan and profile. Let's see if I can kind of zoom in here. So on this one, you can see that there's some elevation differential, right? There's definitely a lot of elevation differential from one side to the other. And in cases like this, we have what we call a section of dry hole, because the drilling fluid in the hole is going to drain down to the slowest point. So you're never really going to be able to keep this hole filled from about this point, which we call the fluid equilibrium point, up to the exit point here. So what this section of hole in is critical. Is it going to be stable without any drilling fluid in it? Well, if it's rock, you probably have a pretty good shot. If it's soil, maybe not. Just depends on what kind of soil, how dense it is. If it's glacial till, let's say, highly overconsolidated, might be fine. The other question is, what's the risk of groundwater influx into the hole? If there's no drilling fluid in here to kind of keep the water out, are you going to have a bunch of water coming in? There's just some of the considerations you need to think about when you have these drills that are have a elevation differential like this. Again,
Mark,
you can, yes.
can I ask a quick question? Someone said, while you are presenting on uneven profiles, can you address the maximum differential head elevations possible functionally doable for HDD profiles?
Yeah, so I think the most that I've seen, it was 400 and something feet. It was in Wyoming. Well, no, was it Wyoming? Yes, Wyoming, in a fairly soft rock formation. That the groundwater table is relatively deep, so we didn't have to worry about the influx of water. So it just depends. There are some things, other things don't really have time to get into, but as far as like pressure on the pipe, when you're pulling the pipe, it's under pressure from the drilling fluid around it, and as the drilling fluid backs up to the higher side of the crossing, all of a sudden the exterior pressure from the drilling fluid on the pipe can be pretty high, which can collapse a pipe. The things you need to look at, but it is possible to 400 or 500 feet, but there's potential for a lot of risk there. So
There's one more question, and I'll read it too, and if you want to address it later, that's fine. It just said, can you discuss some of the risks and challenges associated with mixed soil / rock conditions? For example, rock outcrop unavoidable within mostly soil alignment.
yeah, it's at those soil and rock transitions that you can have problems because if you've got some section of the hole's rock, you're going to have to use rock hole opener, like I showed earlier. Those things are really heavy. And, particularly for larger diameter crossings, you're going to run multiple ream passes through there. Well, in order to get to the rock, you've got to go through the soil. Well, what happens is those heavier tools they sink down in the soil. So every pass through there with an increasingly larger reamer kind of chews its way down a little bit, kind of creates more of an egg-shaped hole we call key seating. And so when it gets to the rock, it's not going to be perfectly lined up with the hole that was drilled from the previous pass or reamed from the previous pass. So you can get these ledges form when you're going from soil into rock. If you're going from rock into soil, the reamer is passing from rock to soil, it's less likely to happen because you're pulling it out of the rock into the soil and not downhill into the rock. So, yeah, it's definitely one thing I kind of recommend is on the exit side of a crossing, the pipe side where you're going to be pulling the pipe into. If you can, it's actually better to try to ream rock from the entry side to the exit side so that you don't get that key seating effect nearly so badly to where, I don't know how many projects we've seen where a pipe goes in through the soil section of the hole, gets to the rock, and it like hits a wall, right? Because there's this offset in the hole because of the key seating action of these big hole openers. So, I mean, you could case down to the rock potentially, but you're talking about large diameter casing, it's expensive. There's things you can do, but then it's a cost versus benefit ratio. And ultimately it's up to the contractor. Essentially, what you need to be able to do is be able to characterize the potential for these risks, let the contractor know, and let them decide how they want to mitigate that, if at all. And definitely other thing I would say is if you're going to be in rock, try to stay in rock the whole way. Don't go in and out of rock multiple times. You don't want to design your profile right above the rock because that rock surface may not be consistent between borings. It may look the same elevation between borings, but there could be some variability there. And definitely don't want to be skipping across the top of the rock because that's going to make for some very inconsistent hole geometry. The profile could kind of go up and down and up and down, and pulling the pipe through there could be kind of difficult, if not impossible. So hopefully that answers that. Yeah, so I mean, this is another project. We're trying to fit a new pipe inside of an existing corridor as much as possible. And so in this case, you've got a couple horizontal curves again. It can be done, but unless you have to, don't do it. But in this case, we kind of, because of the right of way constraints we kind of had to. This is that cheat sheet that I was talking about earlier. I've got here on my screen. We can get you some of these if you request, and we have them for different size pipes. This would be for like steel pipe. We have some for HDPE, different diameters. We've got several different versions of this that we can provide if needed. But it kind of gives you, for a 20-inch pipe, typical standard design radius, 2,000-foot design radius, minimum wall thickness, which is based on a diameter thickness ratio of, I believe, 50. Yeah. So when it comes to diameter thickness ratio for HDs, we don't like to see over 60 because at that point, the pipe becomes thin enough relative to the diameter that it's more prone to buckling during installation. And so if we keep it less than 60, less probable that there might be a problem during pullback. HML, horizontal minimum length. So for that 20-inch, looking at about 930 feet. Now this was standard 10-degree entry, 8-degree exit. You can get it shorter if you need to, but these are just places to start. And then it kind of gives you a minimum depth. So minimum depth about 41 feet, which, if you're crossing, a shallow stream or something, that might be fine. If you're crossing a deep river, well, then you're going to have to be deeper, which means you're going to be longer. So workspaces, this is a nice big workspace, about 200 by 300 or something. I don't know, but got frac tanks over here in the corner. You got a cleaning system and a drilling fluid pump over here. You got all your bentonite, pallets of bentonite stacked up. You got enough room for tanker trucks to come in and deliver water. Drill pipe on trailers, and you got tool van over here and a drill rig and a drill cab and a power unit. So this is nice. This is what you'd like to have on most crossings. But, on smaller projects, you just might not have that. Here, they had to close this lane down occasionally during construction for different activities and whatnot. Not necessarily ideal, but you can configure equipment a lot of ways to use less workspace or kind of unconventional shapes. There's another one. That's that one in Michigan where they bought that piece of property and demoed the homes. And I mean, they had residential properties on either side, so they built these sound walls on both sides to kind of, keep the neighbors from getting too angry at us. And here's everything set up. It's a big 860,000 pound, 880,000 pound rig. You can create a workspace in the marsh. In this particular case, they put down some woven geotextile fabric, and then they take these laminated mats and they overlapped them. They overlapped the seams, which made a nice stable working platform, even though this is pretty marshy material out here. That's Sabine Pass, Texas, out in the background there. The other thing to think about is, installation loads and stress calculations. Something that's important to do. So, one thing is, how much is it going to take to install this thing? What kind of pull force? How big of a drill rig? Maybe not necessarily your concern, but you still need to understand what those forces might be and what the stresses in the pipe might be, because you don't want the pipe to be overstressed during pullback. So what we do is we typically look at different drilling fluid weights downhole. So we got 9.5 pounds, 12 pounds, and 10.5 pounds. You can do whatever you want, but it's 9.5 to 12 is kind of a good range for what you might expect. It can be higher, not much lower, not much higher, but and we also look at buoyancy conditions. So on larger diameter pipes, even steel pipes, they're going to be buoyant in drilling fluid. The pull head's sealed, so the pipe isn't going to get drilling fluid in it. So we look at different buoyancy conditions, either empty or full of water, or we run a case, just kind of best case scenario, saying you can achieve neutral buoyancy. And we look at basically the effective pipe weight with and without buoyancy control. So you can see, empty, it's negative, it wants to float, and you can see it's quite a bit lighter. The buoyancy is quite a bit higher in 12-pound drilling fluid versus 9.5. And you can see the pull force, it increases by 100 and what is that, about 140, 138,000, no, 238,000 pounds, 9.5 pound empty versus 12-pound empty. So adding water, you can see can help a lot. Like for the 12-pound empty case, you have 830,000 pounds, 12 pounds full. You fill that thing with water, we anticipate something less than 400,000. So less than half the pull force. This is for a 48-inch pipe, so it's big and going to be very buoyant. The other thing we look at is operating stresses. I mean, ultimately, at the end of the day, the pipe has to, go into service and have some pressure in it. We typically deal with, oil or gas or some other sort of refined products, or water. But, the pipe has to be of sufficient specification so that during operations, you're not exceeding any stresses by codes. Then we talk about hydraulic fracture analysis. I've talked about it before. Don't really have a lot of time to get into the details of how it's done or the equations or the philosophy behind it. But this is kind of a typical drawing you might expect for an HE. You've got the green line, which we call the formation limit pressure. So, as from entry, along the drill profile from entry to exit, this green line represents theoretically what the formation should be able to take for annular pressure. So you can see here at the peak, we're about 250 psi, and this is a levee crossing here. The red line represents the drilling fluid pressure as you drill, the annular drilling fluid pressure as you drill from one side to the other. Because there's a levee crossing, we modeled this as an intersect where we drill the pilot hole from both sides, which, like I said, if we didn't, there's an entry over here on the right. If we didn't model it that way, you see the drilling fluid pressure goes up. And if we didn't intersect it, that fluid pressure would just keep going up and then slightly taper as you start drilling up to the exit curve. But this helps really reduce those annular pressures by doing that. There's only 2,745-foot crossing. Normally, you probably wouldn't do that and intersect for a short crossing like this, but because of the levee, want to reduce the risk. So essentially, formation limit versus drilling fluid pressure, that ratio is the factor of safety, which is shown on this chart here. Anyway, let's see here. Show this.
We did get one more question. It just says, what's a comfortable minimum radius of curvature of the drill, less than typically 100?
Yeah, so and that's another good way. We're actually having this internal debate internally on, so you have a design radius, and it's an industry standard has always been kind of 100 D, so 20-inch pipe, 2,000-foot radius. But it's always good to provide the contractor with something below that, a minimum allowable radius. So when they're drilling the pilot hole, you want them to be greater than, it's like, okay, yeah, we understand it's 2,000-foot radius, but you can drill tighter, and they are going to drill tighter. We know that. But what's the minimum allowable? And really what you need to do is you really need to look at what's the formation. Is it soft soil, because ultimately at the end of the day, regardless of the geometry of the hole, you got to pull a pipe through it, and so where do you feel comfortable of a radius to pull a given pipe through it? Is it softer soil? Okay, well, maybe you can go a tighter radius. Is it hard rock? where maybe any sort of irregularity in the geometry of the hole or the cross-sectional shape of the hole might create a huge problem. So, maybe on rock, maybe you want to have a higher minimum allowable radius and a higher design radius. It's Unfortunately, there's no really easy, good answer for that. It's going to depend on your subsurface conditions, your pipe specifications, what you're comfortable with, and yeah, there's just no textbook answer for that. I'm sorry.
No, you did a good job. There's one more question. It says for the operational shear stress, is there a standard differential for the installation and operational temperatures dependent on region, but what does a conservative go by?
For installation operational temperatures, can you read that again?
Yeah, it's just asking for the operational shear stress. Is there a standard differential for the installation and operational temperatures? And is there a conservative go by dependent on the region?
Yeah. So one thing we did was we found a chart that kind of shows average ground temperatures throughout the, for kind of constant ground temperatures for the country. So you can kind of understand, what the ground temperature is below ground in different areas. And so you can kind of use that as a, let's say, I like to call it tie-in temperature. Because, yeah, the pipe may be sitting in the sun out on the right of way, but when you pull it into the hole, it's going to eventually acclimatize to the ground temperature, right? And by the time the pipe is tied in and operating, really your differential is kind of whatever you anticipate your ground temperature at that location to be at the time of tie-in and the operating pressure. And obviously, if you're closer to the surface, you're going to have more fluctuation in ground temperatures. So we typically like to get that kind of information from our clients because particularly the operating temperatures, because we don't know, and they typically, I think, try to be a little bit more conservative on the minimum and maximum operating temperature. So if we anticipate ground temperature to be 70 degrees, and the client says, well, the minimum operating temperature is 32 to 120, we'll look at the gap, the difference between the 70-degree tie-in temperature, ground temperature, and the maximum, in this case, it's 50 degrees, versus the minimum operating temperature and the ground temperature. And that in this case is 68 degrees, or I'm sorry, 38 degrees. We would use in our calculations, because there's higher, I guess, delta and thermal stresses, the 50 or the 70 to the 120. So minimum of 70, maximum of 120. So that, yeah, again, I don't know if there's a real good kind of book that you can go to. In the industry, I don't think there's any kind of standard of practice on that. Not that I know of. Maybe there's something that other people use that they kind of use as their own standard, but I kind of explain how we kind of do it. So rely on the clients to give you the minimum, maximum, figure out what you think the ground temperature is based on different maps, and kind of look at the difference between installation maximum and minimum in installation temperature. So anyway, are we good? More questions? Sorry, I'm running out of time.
All right, you're golden. Keep going.
Typical. So design drawing, we looked at this, and we'll look a little bit more of this, but you got some notes down here. We've got what we call our drill data box, which gives the geometry of the crossing. So this will give the contractor and the pilot hole surveyor everything you'll need to know. Actually, I can just go to the next slide. So we got our drill data box here, gives you the geometry of the crossing. Got pilot hole tolerances here, which are going to vary from client to client, most likely. This has two drill data boxes because this one actually has a horizontal curve in it. So we run this drill data box with stationing along the actual curved center line, and one straight line between entry and exit. So it's good to have entry and exit details, kind of close-ups of those, particularly, maybe not in this case, but in some cases when you're in a crowded pipeline corridor and you have a bunch of pipelines adjacent to your entry exit points, it's good to include an entry and exit detail, just so the contractor has an idea. Tie-in details, those are important. Sometimes we do those, sometimes other people do those, but how are you going to tie into that new pipe into the old pipe? And construction observation, it's really good to document what's going on during construction, because if things start to go sideways, you've kind of got a history of what was being done prior to that. So maybe you can kind of flesh out why you're having the current problems you're having. So this is kind of standard field report for us, where we've got kind of a construction status table, gives you, number of shifts spent on each part or each stage of the construction project, how much footage today, how much footage today, percent complete, that sort of thing. And it's pretty detailed. We have kind of a minute by minute entries here. Anytime something goes in or out of the hole, we're documenting that. We also document. It's also good for compliance with plans and specs. Documenting where the entry and exit points are. You can see here, this is a picture of the entry stake, and it has the easting and northing and elevation on it. And it's important to document that and verify with the IFC drawing. We've seen several projects where the maybe the surveyors had an old survey file, stakeout file, and they went out there and something changed by the time the contractor got there. The stakes are in the wrong spot. Not good. It might not be worst thing, but it could be kind of bad. So verify where these stakes are and verify where the bit spuds into the ground relative to the stake. Is the drill set up at the right angle? Also, collecting the pilot hole data and evaluating the radius of curvature. We talked a little bit about that. What's the horizontal and vertical radius of curvature for every joint? In this case, we're doing a 3-joint average. So, is the radius of curvature of the hole looking good? Is it in spec? Is it out of spec? Is there anything we need to worry about? And then also the tolerances. How far. On these magnetic steering tool systems, you'll have a calculated survey based on the inclination azimuth. You also a lot of times have a secondary survey if it's a Paratrack or TrueTrack system. So you can check those against each other. How far above or below? How far left to right of center line are you? This is drawing kind of showing, actually it's pretty good. You can see here, they were a little low here through the bottom tangent, a little low, but they entered, exited basically where they had planned. So kind of gives you an idea. It's pretty straight too. We plotted all those out. So it looks good. This is not so good. This was a job that we had done the drawings for. We didn't have anybody on site. They drilled this with a walkover system, and we got the data after the fact. And we got it like, well, what happened? And I think what happened is the drill bit was getting deep enough that they couldn't pick it up with their walkover system. So it doesn't have the downhole steering tool like I explained earlier. They just walk along the surface and locate it that way. And I think they weren't getting a good reading. So they just said, well, we'll just go shallower, right? And then you have all this mess over here. We had no idea what the heck happened. And, we trying to put the thing relatively deep because they're drilling down the middle of the street. We didn't want to be fracking out in the street, angering the homeowners. And yeah, so you don't want to get the data after the fact and then see this. You're like, oh wow, well, what's that going to do our pipe stresses? Isn't even want to go through the hole? Can you pull the pipe through that? Yeah, and then downhole pressure monitoring. That's important, particularly in these levee projects we talked about. This is actually a directional microtunnel project, but demonstrates that you can monitor and plot annular pressures versus allowable pressures, particularly for something like a levee crossing where the Corps of Engineers is very particular and they don't want you to frack out near their levee. So, documenting all this thing can be very important to try to troubleshoot where things are wrong, maybe try to come up with a solution on how to fix them, that sort of thing. And that was a lot of information crammed into about 55 minutes or so. So, again, I'm available to stick around for questions if people have them. But if something comes up later, you have a thought or a question, feel free to reach out. Yeah, April, any more questions?
Just a comment that it just said thanks for an informative meeting. For next time, it'd be good to what does a good drilling plan look like? Components it should contain and why. There is one question that came in. Do you typically run the as-built stresses? And would you recommend an extra reaming if the alignment is critically off?
We typically wouldn't run stresses on the as-built unless they had broken the minimum radius, because we do our initial calculations assuming that they're going to install this thing at some point down to the minimum allowable radius, so that we choose. So unless they go below that, we typically wouldn't on an as-built. So, and what was the second part of that?
The second part of it was, would you recommend an extra reaming if that alignment is critically off?
Yeah, I mean, obviously, making the hole larger does give the pipe more room to conform to the shape of the hole. You know, I, by how much? It's hard to say. How stiff is the pipe? How if the pipe is super stiff, it's going to want to, it's not going to want to curve as much. So there's a lot of variables in there. But yeah, I mean, it can definitely help a pipe fit through a section where maybe there was a tight radius. I can think of one job in New Jersey. It was all rock, and they intersected the pilot holes. And where they intersected there was like a dog leg right there. And so what they ended up doing was reaming a larger diameter hole from the exit side up through that intersect zone to make that hole larger to help that pipe just give it more room to snake through that dog leg than it normally than would have had otherwise. So and it went well. Yeah, no, I'm sorry. They went from the entry side down to the intersect location. That's right. Yeah, and the pipe survived well, and the coating survived well, so it can definitely help.
Okay. And then there's a question on, do we at Geoengineers include the calculations package as part of our typical deliverable?
Yes, yeah.
And then when do you typically specify the use of casing on the entry tangent?
Um, well, typically I would say, let's say for levee crossings where we have to maintain returns, we have to maintain pressures below allowable limits, or we can get shut down. So use of casing in those cases, or if you don't have a lot of profile depth between the entry point and let's say a road or anything else that you're worried about settlement,
Mhm.
casing that section of the hole, of course, that's going to require large diameter casing. Larger than your largest ream pass. So you can fit all your reamers through that casing. That section hole is completely supported at all times. You don't have to worry about at least during construction settlement along the alignment. Now, most companies don't like their pipes installed in casings, and so they're probably going to want you to remove it. So then there's the question of long-term settlement after installation. That's definitely a thing that can happen. If it's that sensitive thing, you might have to do some post installation grouting, to try to fill that annular space so it doesn't settle after the fact. Or maybe you've got a layer, 10-foot thick layer of bowling ball like material, that you're not so much worried about settlement, but you're never going to keep the hole open during reaming and pullback. Maybe you want to use large diameter casing to support that section of the hole, but it's got to be pretty shallow, in a
Mhm.
fairly thin layer. You're kind of limited on how much large diameter casing you're going to be able to install and then get back out of the ground. So,
Okay. I'm gonna do two more questions and then we'll call it. And if you have follow-up questions, you can obviously email me and I'll loop Mark in. But second to last question is the swab pass purely for removing excess hole debris, or does it also reinforce drill fluid on borehole walls for reinforcement pullback?
I say, I say, it kind of does both, and also by pumping some additional fluid down there while you're not cutting new hole or enlarging the hole, you're lowering the drilling fluid weight, hopefully, So we talked about buoyancy earlier, where heavier drilling fluid is going to make pipes more buoyant, which, depending on what the contractor does with their buoyancy control, may be good or may be bad. But if you are pumping clean fluid during a swab pass, there's a chance you can reduce the drilling fluid weight downhole, which in a particular case might be what you're trying to achieve or might be beneficial. So
And then this is kind of a, I feel like a couple questions here, so hear me out. Uh, The question says, for site-specific investigations, if provided data from a nearby drill, how viable is the information if the data is older, let's assume 5 years, etc., assuming the data is near the proposed center line of the new drill?
Well, I guess that depends on the definition of near. I mean, obviously, if it's within a couple 100 feet, yeah, it's probably reasonable. And two, again, it depends on the region of the country, the local geology, how consistent are the geologic conditions in a given location. If you're in the Gulf Coast region, it's probably gonna be silts, clays, and sands. In what order? Might vary a little bit. But if you're someplace in Pennsylvania, up in Pennsylvania, you can get these old valleys that are full of glacial till. So you can drill one boring over here, you drill 20 feet in glacial till, and you hit rock. You move over a couple 100 feet down the right of way, drill another boring, and you drill 80 feet or you drill 100 feet before you hit bedrock. It's all glacial, so it really depends on where you're at. But if you think you've got fairly consistent geologic conditions, and maybe further away isn't so bad. Maybe at least from an initial standpoint, at least, yeah, it could work.
And then a question that was in the same message was, what are the consequences if there are any, slash, is there a certain time frame where you would consider a new investigation? So just kind of building off your last answer.
Yeah, I mean, I think from a time frame, it's there's not that much difference. I know that we've used as part of some project we're working on right now, we had designed an HDD not adjacent to, but within 750 feet of this new drill. And since it was public information, we used that information as well as a little bit of supplemental. So, we used both. We used some of the previous data that we had done, and we drilled two more borings, on a 6,000 foot crossing. So we just drilled two new borings on a 6,000 foot crossing. So we just reduced what we normally would have done, but we just wanted confirmation because this is for another levee crossing or two levees. So it's like, well, to appease the Corps, we think it's a good idea to at least get borings near the levees on both sides, use that in conjunction with the old data. Again, I guess my answer is it depends, but hopefully that helps.
I mean, I feel like that's a true consultant though, right? Well, it depends.
Yeah.
No, thanks, Mark. You did a great job as always. Thanks for everyone that joined in. I think at one point we had over 125 folks, so really
All
appreciate
right, I went over. I got
it.
wordy.
Yeah, I mean, but we love it. There's some additional questions in the chat. If you feel compelled, feel free to email me and we can have a conversation about those and get you our response to it. If you have ideas for future webinars, let me know. I threw an idea in there that we'll toss around. Thanks for joining us. I'll send out an email by end of week with the recording of this series presentation, as well as the certificate of completion. And we hope that you have a safe and wonderful Thanksgiving and holiday season. Talk to you soon.
See you later.